Welcome to Module 3 of TigerGraph's course on Graph Fundamentals. Module 2 focused on the fundamental capabilities of graph databases, representing, managing, and analyzing relationships between different data entities. Module 3 will look at the evolution of graph databases, from the first commercial products to the present. This module has 3 key objectives. The first is to understand the evolution of the 3 generations of graph databases. The second is to look in more detail at what distinguishes the third generation, the native parallel architecture. And the third objective is to understand the functionality that a native parallel graph delivers. This chart provides a handy outline to the evolution of graph databases. The prehistory of graph databases includes network databases in the 1960s. The Graph 1.0 represents the first commercial graph databases, almost 20 years ago. The best representative of this generation is Neo4j. They provide the basic functionality of a graph database, but they were designed with single server, single-threaded architecture, so speed and scalability are limited. They are fantastic for loading up and visualizing small to medium-sized datasets, but they can't handle the data loading, complex querying, and real-time updates on large datasets in the hundreds of gigabytes to terabytes. The next stage in development addressed the scalability problem by using NoSQL technologies for storage. Graph 2.0 technologies such as data stacks are built on top of key value or column-based stores such as Apache Cassandra. They solve the data loading problem. You can load terabytes of data into Graph 2.0 technology. However, since it doesn't use native graph stores, Graph 2.0 does not perform well at deep link multi-hop queries. Also, due to their NoSQL foundations, they are not designed for real-time updates. When you have a user update, payment transactions, or purchase orders pouring in, it is not possible to update the graph in real time. TigerGraph developed Graph 3.0 to address these deficiencies in Graph 1.0 and 2.0. It again returns to native graph storage, but this time applies parallel and distributed design principles. Not only does the storage scale, but all aspects of the processing, loading, querying, and updates are accelerated and scaled out. Graph 3.0 is the first graph generation capable of HTAP. HTAP stands for Hybrid Transactional and Analytical Processing. This is a term coined by Gartner, specifically bringing together and supporting 2 different paradigms: OLTP, which is Online Transaction Processing, and OLAP, which is Online Analytical Processing. TigerGraph is the first HTAP graph database, supporting both transactional as well as analytical processing with a single schema and instance of the database. This slide points out 6 benefits of TigerGraph's third-generation native parallel graph database technology. Let's start with the scalability at the bottom left-hand side of this chart. TigerGraph has been designed to load massive amounts of data into the database quickly for analysis. TigerGraph can load up to 300 gigabytes of data per machine per hour. A terabyte can be loaded by a single machine in a few hours, or less than an hour with parallel loading into a machine cluster. TigerGraph is live at multiple production systems with billions of entities and tens to hundreds of billions of relationships, with the ability to scale up to 1 trillion or more with additional hardware. Going clockwise, let's look at the next key benefit of third-generation native parallel graphs: real-time transactional workloads. Your business is 24/7 and doesn't stop. New data are created every minute, which includes new customers, suppliers, devices, locations, payments, trips, and other updates. In order to perform analysis on the most up-to-date business data, you need a graph database that is mutable, which means you can update it just as readily as you can read it. Graph 1.0 technology such as Neo4j was never built to be transactional and is not used by clients in that manner. Data stacks and other Graph 2.0 vendors built on top of key-value pair solutions can hold large amounts of data, but are not mutable, which means they aren't able to support transactional updates absorbing new data while responding to queries with complex analysis requirements. TigerGraph is live in production with over billions of transactions per day. Let's talk about the next benefit: real-time performance. The ability to provide sub-second responses to ad hoc queries, which might be tough with tens of millions of entities and relationships. Queries on Graph 1.0 and 2.0 technologies often take a long time or time out, especially if they grow across the entire graph, touching a large number of entities and relationships. TigerGraph is deployed in production with sub-second response times for complex queries at multiple clients in financial services, e-commerce, and healthcare. Coming over to the right-hand side of the chart, let's talk about deep link analytics. This is the ability to go through 3 to 10 plus hops, computing and analyzing across the graph to provide non-obvious relationships among nodes to uncover fraud, find money laundering activities, or create compelling product recommendations for e-commerce that go beyond the usual 2-hop analysis. Graph 2.0 technologies aren't able to deliver analytics beyond 2 to 3 hops for large-scale graphs in a reasonable amount of time. Deep link queries will run out of memory or simply time out due to architectural constraints of these systems. TigerGraph is in production for deep link analytics spanning large graphs with hundreds of billions of entities, detecting fraudsters and mobile networks, ride-sharing companies, and identifying complex payment transactions that are likely to be involved in money laundering. Now let's talk about how easy it is to develop complex real-time deep link graph analytics with TigerGraph. GSQL, the query language for TigerGraph, is easy to learn, and it's easy to develop complex graph queries with minimal effort in only hours or days. GSQL includes not only querying, but analytics and data loading. Queries automatically create RESTful endpoints and deliver data in JSON or CSV format, which makes integration easy and universal. GSQL is easy to use for developing data exports, for sharing the query with business user-facing tools such as BI, and as well as for feeding machine learning tools with new training data. Lastly, we come to an important aspect, especially for consumer rights: the need for privacy for sensitive data, especially with consumer data privacy regulations such as GDPR, the General Data Protection Regulation, or the California Consumer Privacy Act. TigerGraph is built for protecting the privacy of sensitive data to allow users, departments, or organizations with the right privileges to view and update sensitive data, such as social security numbers, date of births, medical records, etc., while ensuring that other users, departments, or organizations cannot view or update sensitive data. Let's look at key differentiators for third-generation graph. TigerGraph is the world's first native parallel and distributed graph. Its architecture is designed for interoperability, has a user-extensible graph algorithms library, provides multi-graph service, has its own query language, GSQL, which is Turing complete and easy to learn, and has GraphStudio, a comprehensive visual software development kit for end-to-end graph design, deployment, and exploration use cases, and allows for machine learning feature generation. So what makes TigerGraph so fast and scalable? The answer is being designed from the ground up as a native parallel graph according to a massively parallel processing or MPP paradigm. Native graph storage allows for rapid index-free traversal from one entity to another. A parallel graph computation engine allows multiple threads to traverse the graph, enabling real-time deep link analysis across graphs with tens to hundreds of billions of entities and relationships. TigerGraph incorporates data compression into a ground-up native storage design, resulting in as much as 10 times compression for datasets with attribute-rich vertices. Compression means smaller footprint, which means lower cost of ownership for you. TigerGraph scales up with additional CPUs on a machine and scales out by distributing a large graph across multiple machines. TigerGraph supports database sharding, which means a large graph with 1 terabyte of data can be automatically partitioned into 10 machines with 100 gigabytes of data per machine. Queries read and write from any or all partitions in real time with no effort from the user. Let's dig a little deeper into the computational parallelism powered by MPP in TigerGraph. Each vertex, as well as edge, is not only a unit of storage, but also is a computational unit. Each unit, vertex, as well as edge is processed in parallel, and the TigerGraph engine will automatically scale the computation across all threads and CPU cores available. Let's consider a customer deployment to see how this works. One TigerGraph customer has 6.6 terabytes of input data, resulting in 20 billion vertices, 95 billion edges with several attributes on each. To handle the deep link queries up to 11 hops and to achieve response times around 100 milliseconds, they chose machines with several CPU cores, giving the MPP engine the resources to work with. 16 or 32 cores are a common choice. To handle the large data size, it is not economical to try to put all the data on one massive machine. Instead, it is less expensive and higher performing to shard the data across multiple machines. Due to data compression, they only needed 4 machines with 128 gigabytes of RAM each. This system handles up to 2,300 queries per second. TigerGraph is designed for interoperability. Its architecture is designed for deployment either on the cloud or on premises on standard Linux services. TigerGraph is available on AWS, Microsoft Azure, and Google Cloud Platform GCP marketplaces. TigerGraph supports Docker as well as Kubernetes containerization and has built out a large open source library of connectors to popular data sources, including Spark, relational databases, Kafka-based streaming, Amazon S3 buckets, and Hadoop. The GSQL language includes high-level data loading commands, with built-in ETL functions to simplify data loading. TigerGraph's real-time deep link analytics is available via RESTful APIs for queries as well as for real-time transactional data updates, supporting a fully mutable transactional graph. TigerGraph has built a rich repository of popular graph algorithms, including PageRank, community detection, k-nearest neighbors for machine learning, shortest path, closeness centrality, similarity, etc. First-generation graph databases such as Neo4j provide graph algorithm libraries as well. However, TigerGraph's graph algorithm library is fully user-extensible. It is written in GSQL, TigerGraph's graph query language, which is Turing-complete and closely modeled after SQL to allow SQL developers to learn it in hours. Neo4j's APOC graph algorithm library comprises of pre-compiled Java function calls, so the users can't modify the algorithm steps or parameters. TigerGraph's graph algorithm library is fully customizable and extensible, allowing the users to add or modify the input parameters, edit their algorithm steps, and modify the output or data updates. MultiGraph allows organizations to enforce privacy and security for sensitive data such as social security numbers, national ID numbers, and financial information. The entire graph can be segmented into specific subgraphs, allowing users who are assigned a specific role to access data which are approved for that role, while restricting access to data which are not approved for that role. This is a key requirement, especially for compliance with the California Consumer Privacy Act and other laws in the United States, and the GDPR regulation in Europe. GSQL is TigerGraph's graph query language. It takes the best ideas from earlier languages, SQL, Cypher, Gremlin, and Sparkle, to synthesize a language which is both powerful and easy to learn for the full range of graph applications, not just pattern matching, but graph algorithms, transactions, deep link analytics, and future extraction for machine learning. GSQL is Turing complete, allowing the developers full flexibility to code any algorithm with GSQL. Built-in semantics allows for parallel execution in TigerGraph's massively parallel processing, or MPP engine. GSQL has special features called accumulators, which make it easy to employ MapReduce like aggregation and computation. If you are interested in learning how GSQL compares to Apache Tinkerpop Gremlin, or other Turing-complete graph query language, or Neo4j Cypher, you can find a white paper at info.tigergraph.com/GSQL. GraphStudio is a full end-to-end visual software development kit for graphs. With GraphStudio, you can visually create a graph schema, map data sources to each vertex and edge in the schema, load up datasets with billions of entities and relationships, and explore the data visually. You can try TigerGraph's GraphStudio yourself at tigergraph.com/testdrive, where we have several demos for popular use cases such as fraud detection and social connections analysis, with large datasets preloaded into TigerGraph instances on the cloud. GraphStudio also allows developers and data scientists to write and run queries, explore their output, and perform ad hoc analysis on the dataset. TigerGraph's GraphStudio is used by fraud investigators, merchandisers, and business analysts for ad hoc analysis and exploration of connected data. Given TigerGraph's query language and engine designed to handle graph analytics at scale, it is a great vehicle for machine learning using graph-based features. Consider a real-world example from a mobile service provider where graph-based features for machine learning are generated in real time and used to improve detection of fraudsters who buy prepaid SIM calls and scam people out of money. Phone-based fraud, especially during using prepaid SIM cards, is very hard to detect with traditional analysis, as the prepaid SIM cards often do not have a lot of information about the customer, such as their real name, address, phone number, and their driver license, passport, or national ID number. Fraudulent behavior must be detected by analyzing the behavior of a phone with other phones, and the detection needs to be in real time to ensure that fraudsters are stopped as soon as possible. This problem is a perfect fit for a native parallel graph database such as TigerGraph. Let's look at how TigerGraph identifies features by analyzing relationships among phones to identify what is a good phone, a phone that belongs to a regular customer, and what is a bad phone, a phone likely to be involved in a scam. This telecom company uses 118 graph features from a sample of their hundreds of millions of customers to train their machine learning system. The figures here illustrate a few of those features. One feature is, a customer with a good phone calls other customers and the majority of the calls are returned, indicating familiarity or a trusted relationship. 2. A good phone also regularly calls a set of phones every week or month, and this group of phones is fairly stable over a period of time. Phones in this customer stable group also call each other, making so-called in-group calls. Lastly, a good phone is often involved in 3-4 step friend connections, which means the good phone calls another phone, phone 2, which calls phone 3. The good phone is also in touch with direct calls with phone 3. This indicates a 3-step friend connection, indicating a circle of trust and interconnectedness. Conversely, phone scammers tend to blast out huge numbers of calls, with few calls returned. They tend not to have stable groups. Not all features so clearly distinguish good or bad behavior. The purpose of machine learning system is to do the statistical heavy lifting to tell us which features in fact associate the good or bad behavior. Like any program, the quality of machine learning output depends on the quality of the input. Graphs embody features which are not accessible or even considered of from more traditional tabular data. By using graph-based features for machine learning, users can greatly increase the quality of their machine learning input, yielding better machine learning output. We've covered a lot of material, but there are just a few key points you need to remember. Graph databases evolved over the last 2 decades in 3 generations. Graph 1.0 is characterized by native graph storage, non-parallel processing, and no database sharding, which means it can't spread a very large database across multiple machines. Graph 2.0 is characterized by a graph built on top of a key value or column store. It supports distributed storage but is not efficient at graph queries or analytics more than 2 hops deep. Graph 3.0 is the latest development, features native graph storage, parallel processing, full database sharding, and real-time updates to support transactional as well as deep analytical workloads with 10 plus levels or hops in real time. TigerGraph, a native parallel graph, provides 7 key differentiators. It is the world's first native parallel graph. Its architecture is designed for interoperability. It has a user-extensible graph algorithms library. It allows for multi-graph service, and it has its own graph query language, GSQL, which is Turing complete and easy to learn. It has GraphStudio, which is comprehensive visual software development kit for end-to-end graph design, deployment, and exploration use cases. It allows for machine learning feature generation. Here are some sample questions that you should keep in mind before you take the online quiz. How is the data stored in a first generation graph database? How is the data stored in a second generation graph database? Which of the following generation of graph databases supports database sharding, the ability to distribute a terabyte of data across 5 machines with 200 gigabytes of data in each machine? Which generation of graph databases supports deep link analytics on very large graphs? Which generation of graph databases support real-time collaboration and secure sharing of data where multiple groups share one master database without duplication of the data?